So Paul, please, it's your turn to introduce.
Terrific. Well, I'm delighted to introduce Ting Zhang, who you just met. He's a professor at the Suzhou Institute of Nanotech and Nanobionics, or SciNano. He's an editor of the journal Microsystems and Nanoengineering, is on the National MEMS Technical Committee for Standardization of MEMS Technology. He's won many awards, including the Young Talented Scientist Award from the China Instrument and Control Society and the Six Talent Peaks Project in Jiangsu province. So, Professor Zhang, the floor is yours.
Thank you very much, Paul. Okay, I will start with my talk. Can you see my screen?
Yes.
Okay, great. So friends from the iCANX talks, good morning, good afternoon, and good evening, and Happy New Year. So today it's my great honor to share with you our recent progress on the flexible sensing electronics. Today I'm not only talk about some basic research result. I also like to talk about some engineering process and the real applications. So I think we all are willing to see if it's possible to make the flexible sensing devices to make it to the real applications. So first, I like to introduce the location I'm working in now. Is at the Suzhou city. It's called the Paradise of China. It's very close to Shanghai, with about 2,500 years of the history and rich culture, beautiful water gathering. And if you come to the Suzhou in the spring, it's very beautiful. I all welcome you come to the Suzhou for the communication and also for the entertainment. And also it's very modern, you know, it already become one of the largest industrial nanotech industrial ecosystem in the world. So it are integrating the key resources from the university, the institute, and also the investment on also the industries. So it's really a good place for the nanotech industry. So our institute is called the Suzhou Institute of Nanotech and Nanobionics. We call it CNano at the Chinese Academy of Science, and it's located in the beautiful Suzhou city. And this is the website of our research group. So the main research area of our group is for the smart development of the smart materials, flexible and stretchable electronics, wearable electronics, and also the MEMS devices. Also, we have about more than 20 students and also staff interdisciplinary research groups, and we explore this material and the device application in the healthcare, IoTs, and also the neuroprosthetics, etc. So the content of my talk today is in the following part. First, I give the introduction and the motivation, and also I give you our design strategy for the flexible sensing electronics. And also for the multifunctional flexible and stretchable sensors based on the nanostructure and the molecular structure designs. And also, finally, I will give you some engineered flexible sensors, our engineering process for the real applications. So recently, driven by the global demand for the smart systems, sensor has become an active research and development field. In the year of the 2013, the T-Sensor Summit conference reaching the potential to fuel sensor market growth through trainings within a decade. From this figure, it was predicted as abundance based on the prediction from the big companies such as Bosch, HP, and Intel, etc. And there's two main streams for the sensors currently. One is based on the MEMS fabrication process. It's called the MEMS sensors, and also the other is kind of provide with more function of the flexible, which can conformably attached to the soft or curved surface. And these are the two main streams for the beyond Moore's law age, and provide more functionality and diversifications for our smart cities and also our societies. So in our research group, we did some progress on the both directions for the MEMS sensor and the sensor arrays in our group. Our students and the research staff can develop the microsensors based on the functionalized nanomaterials and also the MEMS fabrication techniques. In our institute, we have the one of the largest the MEMS foundry, R&D foundry in China. So we can do the simulation and the design and fabrication by ourselves. So in our group, we mainly focus on the chemical and also the bio microsensors. Because with the MEMS technique, the sensor can make very small. So when combined with the flexible circuit or the stretchable circuit, we can also get the hybrid sensing solutions. And we are not only do the fundamental research, and also we are trying to get to the applications with the engineering process. Here, I give you a quick example is that we started the environmental gas sensor microsensor project at the year of the 2013 based on the MEMS hot plate. Its size about 1 × 1 millimeter squares. And then in the center, there's a 5 micrometer thick, the floating membrane with the heating electrode and also the sensing electrode. So we started this project at the 2-inch wafers in our facilities. And after 3 years, we moved our design to the foundry to start to scale up this manufacturing. Then we collaborated with our industrial partners, and about 1.5 years, we got the real product. And it's really a long and also iterative process. From here, you can see we have to, the devil is really in the details. We are not only have to solve the bottleneck of the MEMS micro hot plate the design and fabrication. Also, we have to get the nanomaterial sensing materials uniform the dispersions, and also how to accurately deposit these materials in the center of the chips. On the 6-inch wafers, there's about 15,000 chips on these wafers. We have to make every deposition very uniform and very in the accurate locations. Combined with this effective packaging, then after we go through all these processes, then the industrial partners will take over and start to the commercialization these technologies. And for the flexible and the stretchable sensing electronics, they are an exciting frontier for the next generation of the, for example, the portable or the wearable electronic devices. If you search the flexible electronics at the Web of Science in the last about 10 years, you can see that the publication number is fastly grows. And also the publication from China is a big player in this field. And also, it already have a very good global flexible electronics market. The compound annual growth rate is about 21%. And the largest the market is in Asia currently. And also, if you see it by the applications, the consumer electronics will be the largest part because it have large quantities. Also, it have the many applications in the automotive and the medical and the healthcare and the energy and the power application field. And even for the bright futures, but there still have many challenges for the flexible sensing electronics. For example, it have the limited sensing performance usually under the flexible or stretchable the conditions, because it usually require the flexible or stretchable substrate. It will cause sometimes the no sensitivity and the no response time, and also the recovery time, and also have the hysteresis. And another very important thing is that they usually have the low stability due to the mechanical mismatch at the interface of the materials, the electrode, and also the substrate. So it's a very, very important thing to when this flexible sensing electronics go to the applications. And we have some, we proposed our design strategy for the flexible sensing electronics is to combine of the functionalized the nanomaterials and the regional design of the micro and the nano and even the also the molecular structures. We utilize the unique flexibility of the materials and the structure design, and we're trying to achieve with the high sensitivity and the high stability, and also these good properties of these sensing devices. And based on this principle, we developed a series of the flexible mechanical sensors with high sensitivities. For example, for the flexible electronic skins, we get the very low detection limit, about 0.6 par. And for the acoustic signal detections, we call the flexible bionic eardrums, we get the wide range of the detection frequencies. And for the shear force detection, we call the flexible fingerprint. We get a very accurate texture of the surface to detect. So in the following slides, I will describe our progress on these directions. And from this simulation, we can see that if you design a means of the microstructure at the interface of the flexible devices and cover them with some very thin nanomaterials, for example, the single-wall carbon nanotubes networks. And based on this simulation on the model, we can see that there have the stress concentration effect at the interface. So the stress of the microstructure interface will increase about the 3 orders of magnitude, which will dramatically increase the contact resistance change, even under a very tiny pressure or pressure change. And for the sensing material point, we usually like the carbon nanomaterials, including the carbon nanotubes, and also the graphene, and also even the conducting carbon black. And here we developed a process which can at the liquid and the gas surface to layer by layer exfoliation of the ultra thin of the carbon nanotubes. It was governed by the Young's law at the surface chemistry. The surface tension of your solvent plays a very important role, which we get. You can see here that we get the very clean and the network of the carbon nanotubes, single carbon nanotubes. The thickness about the 20 to 30 nanometers. So we cover this carbon nanotube network with these pyramid structures, and we assembling as a double layered piezoresistive devices, so we can get a very high sensitivity at the pressure. For example, we put an aunt on these devices, so we can get a very fast and also the sensitive detection of this weight and the pressure. And for this material, we just put on our fingers. So you can see here that it can monitor your heart rate in the real time. And this signal have a very good signal to noise ratio, which can be transferred to the pad or the cell phone, the terminals, etc. And with these devices, we can measure the real-time physiological signals. For example, we can continuously monitor the pulse signals, and this data for the healthy and the pregnant lady. You can see that through the pattern recognition, you can tell that the body condition is not the same. Also, when you attach on the neck, you can, during your speak at the low frequency talk, you can measure the muscle movement and for the voice recognitions. So for the low frequency signals such as heart rate and the pulse and also your speak, it's okay for the device. But for the high frequency signals, such as the acoustic the signals above the 1000 hertz, we have to optimize this device. So in this work, we developed this device we call the flexible electronic eardrums, and we developed the mathematical models and at the interface of these devices. And we found that the micro pattern, the size, and also the strain state, and also the thickness, it plays a very important role. We did the experiment to verify these parameters. Then we optimized these parameters, so we get a very high signal to noise ratio to the acoustic signals, also with a wide frequency response range, and it can be utilized to for the voice recognition about the people speak, and even record the people talk. Another very important force is called the shear force, which is very important for the, for example, for you holding a stuff for the bottles, and it plays a very important role. Also, it can feel the surface textures and the roughness of your surface. And governing the physical law governing behind that is a frequency, is a correlation with scanning the velocity and also the waveform of your surface textures. So we developed our double layer device. We add another layer of pyramid, the structure at the bottoms. And when we developed this equation, and also when we scan over the the very tiny objectives, so we can transform this voltage domain signal to the frequency domain signals. In this case, we can get the characteristics frequency signals. For example, when we scan cartons with a different size of the textures, we can use the characteristic frequency to tell the surface texture of the textiles. And with this microstructure design, we developed a series of different types of flexible mechanical sensors. For example, this we use micro patterned PS layer as a dielectrics to make as a capacitive pressure sensor. We get the extended the sensing sensing range of this microstructure sensor compared to the non-patterned sensors. And also we use the CVD growth method to get the cracked graphene growth on the two electrode, which is have the selective sensing to the strain directions. And also we developed the hollow conducting polymer such as polypero microsphere based pressure sensors. In here, we cross 3D cross-linked the carbon nanorods with how many the chemical and also the physical bond in the between is very sensitive to vibration. So we investigated the, in the Parkinson disease to test these rest tremors in these applications. With these microstructural designs, the following I will talk about in a complete story how we design in the systems and to meet the requirement. For example, in this work, we trying to restore the lateral sense of the touch. In the neuroprosthetic system diagrams, the flexible sensors assembled on the prosthetic hand provide the front-end sensory signals for substantial signal encoding, transmission, and the neural interfacing. So the flexible sensors can result in the generation of the bionic tactical informations. However, currently the abandonment rate of the prosthetic hand is still high because the traditional prosthetic hand is a single function and also the lack of the tactical perception and feedback. This traditional prosthetic hand are not dexterous enough to manipulate the objectives in the practice and limited by the unknown informations such as the slippery and the weight perceptions. So we are trying to develop in the project, develop the smart prosthetic hand, and so use sliding friction force. We found it's a critical criterion governing whether the hand can be grab the objective steadily. And also the static friction force is crucial for people to estimate the weight of the object in hand. In this case, the detection of the static and the sliding friction force is very necessary for the textural in-hand manipulations. And how does the human skin perceive the multiple types of the forces? And from here, we can see that on our fingerprint, there's 4 types of the mechanoreceptors. And among them, for the rough endings, which can be the selectively sensitive to the shear force and due to the stretching of your skins. And this signal can put as an acting potential to commute to the brain systems. So benefiting from this rough endings, so our fingerprint or our hand can select sensitively to the static and the sliding friction force during the object manipulations. So inspired by this biological skins and the fingerprint, our approach is to develop the rough ending inspired the highly selective flexible friction force sensor, and also to develop the signal encoding circuit to restore the slippery perceptions. This is the design and the fabrication of our device. From here, you can see that the silver nanowires was spray coated onto the silicon wafer mold, and then the silver nanowires on the top layer of the silicon mold was removed. Through the replication process, the silver nanowires was embedded to the surface of the 3D the PDMS microcolumns, and there's no silver nanowires exited between the microcolumns. And finally, the silicon rubber from the EcoFlex was explored as a dielectric to fill the grooves between the microcolumns to make this device. And we did the finite element simulation analysis. So due to the lower Young's modulus of the EcoFlex compared to that of the PDMS, the microcolumn electrode can be easily deformed under the shear force. So when only the normal force applied, there no obvious deformation of electrode was observed. But under the sliding friction force, electrode was laterally bended but not stretched. Conversely, when the static friction force was applied, there's no relative displacement at the contact surface, and the electrode was laterally stretched. And then we did the experiment to verify this result. Here you can see that with a setup the apparatus, the figure shows a real-time response curve under the normal static friction and the sliding force. And these results agree well with our simulation result. And how does the deformation affect the capacitance of the sensors? We analyzed the coupling between the solid mechanics and also electrostatics. For the static friction force, the effective overlapping area increased during the loading static friction force, which causing the increased capacitance. And conversely, the capacitance decreased under the sliding mode due to the decrease of the effective overlapping areas. And then we did some demonstration. We put this sensor, the friction force sensor, on our gloves. When we scan over the weight, we can see that real-time the capacitance is decreased. It's good for the slippery detection. And we also put on the robot hand. There's no movement. So when we put in the water in the bottles, we can see that there's a static friction force increase, which is good for the weight perceptions. And when we put the weight on the top vertically on the our devices, we can see that there's a negligible sensitivity to the normal force. And to regenerate the slippery perception of these neuroprosthetics, a signal encoding circuit was designed for the bionic stimulus response signals, which is helpful to transmit the analog signals from the sensors and such the capacitance and to the nerve issues. So according to this signal encoding circuit, the frequency of the resulting the bionic pulse signal was modulated by the applied sliding friction force. From this figure, we can see that the signal response under the different sliding friction loadings the spike frequency increase as the capacitance decrease due to the slippery. So through this design, the circuit and the frequency range and the variation trend of the sensors are able to achieve similar result to the human response to the force stimulus, and which potentially can apply in the restore of the slippery perception in the neuromorphic systems. And so in the about part, I talk about our proposed design strategy for the flexible sensors, and also I give you one complete story of the its application and design in the smart prosthetic hand. In the following part, I will talk about the how we achieve the multifunctional flexible stretchable sensors based on the nano structure design and also the molecular structure designs. For example, when people ask me for the wearable sensors, they also ask me, hey, can you make these sensors waterproofable when you apply on your bodies? So in this work, we developed the super hydrophobic films, also can be used as the wearable sensing sensors. And this method is developed by our one patent spreading method. We use carbon nanotubes dispersed as a thermoplastic elastomer and with cyclohexene as a solvent to achieve the very uniform dispersion, and are also very stable, and it can stable for about 3 months. Then we spray printing on the surface. After drying, we use acetone to etch in these films. Then we can create the gradient distributed the composite materials. Composite material, and with a very rough surface, with increase the surface roughness and also the air frictions. So it gives the property of the super hydrophobicities. And from the cross section of the image, you can see that there's a gradient distribution of the carbon nanotubes and also the thermoplastic elastomer composite. About the several, a few micrometer thick of the composite films, you can see that on the top there's a micro holes of these structures, and also on the top there's a nanoscales of protuberance at the surface, and in the middle there's a thermoplastic elastomers partially coated with the carbon nanotubes, which is very sensitive to the strain sensing. And at the bottom there's have the more thermoplastic elastomers, so it can reinforce the adhesion with the substrate. And the contact angle of this water drops is larger than 150 degrees, so it have the super hydrophobic properties. And this structure also very stable. You can see here that we tested its mechanical stability and also its chemical stability. That after loading the 300 times, when these films was combined with cottons, it still have the very good hydrophobicity properties. And also we etching with the acrylic stress and also the acid stress and the UV stress, and you can see that it still have the contact angle still larger than 150 degrees, which shows the very good the chemical stabilities. And then we make it as the waterproof the wearable sensors, and we can patent coated the printed on the glove or the clothes. And you can see that it have the very good sensitivity. Even you drop the water on your sensors, there's no interference with your signals. Very high resolutions and a very fast response time, about 8 milliseconds. And here we also put in the this hydrophobic coating combined with magnetic nanoparticles, so it can make it as a micro robot, which can easily floating on the flow surface. the water surface. And with these films, we use the pre-stretching and the wrapping and releasing strategy. And after we get the carbon nanotube and the thermoplastic films, then we use pre-stretched the thermoplastic wires, and then we wrapping these films on these bodies. After we release, we can get the ordered micro barcodes on its surface. And this surface can make the barcode cold shell, the ultra stretchable, the fiber sensors. You can see that it at the different stage, at the stretched stage, up to about 11 times. And the structure is very stable, and it's also very sensitive to the strain change. And due to the contact, the state change of your conducting shells of the camera nanotubes composite films. And this method can also be extended to make the stretchable chemical and biological microsensors. For example, in this work, we developed the stretchable, the electrochemical glucose sensors with programmable sensitivities at a different stretch state, and also for the stretchable VOC chemical sensors. If you are interested, you can look into these two papers. And not only on the micro nanostructure designs, we can also make the multifunctional sensors based on the molecular structure designs. For example, in this work, we developed a moisture-driven power generation and the self-powered sensors based on the polydopamines. We print the water-soluble polydopamine on the at the two electrode, and through the electrochemical reduction and the oxidation on the electrode, we can get the gradient distribution of the hydroxy groups, so that it can capture the moistures. So utilize the chemical potential energy, which widely exists in the spontaneous diffusion processes, such as moisture diffusion, that which can trigger an ion concentration gradient, create the chemical potential energy. And it can work as an energy harvesting layer, and to provide the powers for the, for example, the flexible pressure sensing layers to get the self-powered sensing systems. And it have the very good output power density, about 0.246 milliwatt per centimeter square, and the fast response time, and also very flexible and also the stable. And from here you can see that we don't need any power. We just connect this power generator with this pressure sensor, and we blow the gas to these systems. And after its exposure to the moistures, it start to mirror in your pulse change. Use pressure sensors, and also itself can be the very good for the breath detection, monitoring the moisture change. Here I give you another example based on the molecular structure design. We make the stretchable and the self-healing, also the transient micro molecular elastomer gels. We insert the small molecules glycerol into the hydroxy ethanocellulose to forming micromolecular elastomatic gels. So the dynamic hydrogen bond occurs between the HEC and also chain, and also the guest small glycerol molecules. So it gives you the stretchability about the 300%, and also the self-healing properties under the ambient conditions. And also this elastomer gel is totally the water soluble, and its degradation rate can be toned by the adjusting the HEC molecules and also the ratio of the HEC to the glycerols. So we demonstrated the flexible and stretchable electronic devices such as the self-healing conductors, and also the electronic skin for the robot, etc. And the mechanism is that by inserting the glycerol into the hydroxy inserting this to the HECs, it forms a reversible and dynamical, the weak hydrogen bond, which give it stretchable and self-healing, and also the transient properties. Here you can see some demonstrations. When you put in the water, after about the 15 minutes, it totally degrades in these devices. And with this, all these innovations, and it also leads the really long and take all the details for the flexible sensors for the real applications. For example, you have to go through the surface treatment of the flexible substrate, and you have to prepare the uniform dispersed of the non-conductive inks. And through the high efficient printing process, and combined with the packaging and the algorithm and also the circuit, then you can get the engineered flexible sensors for the real applications. The key process is that first is for the large scale printing process, which there's some key technology we have to go through. For example, the development of the highly uniform dispersion of the conductive or semiconducting ink based on the different sensitive nanomaterials. And also for the surface treatment of the flexible substrate, fabrication of the micro and the nanostructures, and tune their morphology and the property controls. Also, we have developed the high efficient printing process for the large area, large scale manufacturing. And like I said, reliability is very important for its applications. Here, for example, there's one batch of the sensors, about 1,000 flexible sensors. After go through all the process, and we randomly select the 3 devices, and we just go to about the 1 million cycles, repeated cycles, about the 80% load at the 20 loops. You can see that in the beginning about the 60,000 cycles, they have a gradual increase. Then later we find that is because of this shape change of your flexible substrate. Then later it becomes very stable over about the 1 million cycles. So it can be applied in many as about the real product. And there are many details in this process you have to make this device very stable. For example, the interface is very important. From here, you can see that the small bundles of the single carbon nanotubes was tightly adhered to the patterns of the PDMS substrate after the thermal treatment. And because of the strong van der Waals force between the single carbon nanotubes and the PDMS substrate after the thermal treatment, it is energy favorable for the single carbon nanotubes tightly adherent to the substrate instead of the uplifting from the substrate. And from this figure, it shows the SCM of this single carbon PDMS films, the interface without the surface treatment. And there's the protrusive structure of the single carbon nanotubes, which are quite different with tightly attached single carbon nanotubes after thermal treatment. And also, when we treat this interface about the 200 degrees C, at these temperatures, the volatile silicone molecules in the form of the short PDMS chains will form a conformal layer about 2 to 3 nanometers, and to subsequently cross-link to result in the formation of the silicone coating to get a very stable interface. And there's another very important interface we need to take care is electrode. Commonly they use stretchable electrode. Electronics uses electrical interconnect and the iron bridge structures. It achieved very high stretchability, but due to the low intrinsic elastic strain limit of the conventional metals, such as about 0.3% for the coppers, when it recovers, it usually didn't go to the original state. This will impede its stretchable performance. And we know that for the shear elastic alloys, they have the shear elastic properties with extended the percentage, which can potentially use as a stable and also the stretchable electrical interconnect. So in this work, we designed the shear elastic alloys such as nickel and the titanium alloy based the elastic interconnect. Here you can see it have the about the 7.5 ELAPS properties, and we can have the enhanced elastic stretchability and the stabilities. Here you can see the comparison about the nickel titanium alloy with the copper nanowires with the serpentinous structures. When it comes to the original state, the copper the electrode already have the shape change, but for the nickel and the titanium structures, they have the totally reversible process. And also, we can make the stable interconnect with string isolation induced by the in situ geoheating method, especially for some very soft substrate, for example, this PVA substrate. And here you can see that for the gold electrode and the PVA substrate without treatment, it will easily detach and break. And after the fossil in situ geoheating method and benefiting from the precise control of the heating location around the electrode, the crystallization and the enhanced rigidity of the PVA is restricted to the desired areas, which leading to the effective string isolation. So as a result, the flexible electronic devices is able to conformally attach on the skin, which also shows the negligible degradation of the device performance during the deformations. And with all this process and also the details, we can get a very high precision and also the very stable device performance. Here is that one force touch panel we developed and which in the future have the potential to replace the computer panels. We know that the potential for the computer panels, it only have the X and Y direction, give you positions. But with our carbon composite material-based the panels, you can see that it achieves with a high precision, high speed, and also the very high density of the 3D touch panels. It gives a very sensitive and the faster response to your multiple, also the multiple touch for your for the different pressures. It's also being reported about on the news. And with this effort, we did a series. We developed a series of innovative applications. For example, for the we developed about the over 1,000 sensor arrays for the distributed the pressure mapping system, which can mirror your foot pressure distributions. And also we work with a hospital to get the information for the pulse waveform monitoring and for the body condition assessment. Also, it can use for the robot controls and also can mirror in the EEG, non-invasive EEG measurement devices, and for the VR and the AR applications. So with this, with all these works, we actively collaborate with our industrial partners. So then we spin off of some our technologies, and we get the some awards such as at the China Innovative Sensor Brand Top 10, and also the China High Tech Fair Excellent the Product Award. And then we continuous work on the different microsystems, and also with this algorithm and also for the smart system applications. For example, used for the smart car seat and smart glove for the gesture recognitions, and also the flexible sensors for the wireless earphones, and also for the smart sleep lane monitoring waistband, and also for the in-shoe measurement for the pressures. And then we come to our summary that for the flexible sensors or the sensing electronics, we think is still in the very early stage. They have facing many challenges is that have a limited sensing performance under the flexible stretchable conditions, and also the facing the bottleneck of the mechanical mismatch at the interface of the material, electrode, and also substrate. And our strategy is by combining the highly sensitive nanomaterials with the original micro nanomolecular structure designs, and also to realize the real applications. And we developed the large-scale fabrication printing method, and also to achieve the high stability and reliability. And we think that to develop for the real applied the flexible sensors, the devil is in the details. And finally, I like acknowledge our research groups, and also the collaborators, and also the funding support, and wish you and your family a very happy and healthy new year. Thank you very much.
Thank you so much. Terrific.
Thank you.
We have several questions from the audience now. The first is, Professor Zhang, nice work. Why do you choose silicone rubber for the smart hand? Can you compare it with other flexible materials?
Yeah, for the smart hand, I think for the silicone rubbers is not only good for as a flexible substrate, but also this mechanical property is very very stable. It can resist the friction on the rough surface. I think it's very good for the a good flexible substrate for the devices.
Very good. The next question is, thank you for the wonderful talk. I have a question about smart hands. Can the sensory system also sense temperature, humidity, and other chemical and biological signals?
Yeah, thank you. It's very good questions. And for the smart hand, yes, it's very important for the multi-parameter detections. And currently, we applied the force sensors, including the pressure sensor and also the friction sensors. And of course, for its applications, the temperature and the humidity is also very important. And especially for the temperature, I think for the force sensor and the temperature sensor is provide very important information for the prosthetic hand for the grasping. But it will be better if you have the more sensors, more different type of sensors can be integrated in these systems. We also have to think about the power consumption and also the burden from the circuit.
Very good. The next question is on the, oh, I see, it's different than what I have here. Professor Ting, for the stretchable bionic sensor, how do you calibrate it? And what's the uniformity and repeatability of the sensor?
Yeah, it's also very good questions. So we have the force gauge in our lab to calibrate these flexible or stretchable sensors, which can stretch at a different state and measuring its electrical signal changes. And to achieve the uniformity and the repeatability of the sensors, one is a very important thing is that for the repeatability, you have to make your device very reversible. So you have to rationally choose your materials and make the reversible response of your sensor first. And to make the uniformity is very key issue for the applications. Then you have to make a very uniform the dispersion of your nanomaterials, and you developed your printing process to make the very highly uniform the composite films. Then you can get your uniformity of the sensors.
Mm-hmm. Actually, okay, well, I'll ask a question at the end here. And another question is about the moisture-driven power generator. How do you control that, and can it be overloaded in some way?
Yeah, it's also a very good question. And I think to control the power generator, I think the question is asked, can we get our desired performance of these generators? And we can the mechanism is that you capture the moisture, use a gradient distributed the hydroxy groups across these two electrodes, and to generate the gradient ion concentrations. This is a principle behind this design of this nano generators. And to control is you have to optimize these parameters, such as your concentration of your hydroxy groups, and also your thickness of your films, and also the pore size of these films, and the distance of this electrode. There's many parameters have to be controlled. And I didn't see it's overloading with even we use this very condensated, when we blow all over these devices, it still works. So I didn't see it's overloaded problems.
Very good. And the next question is about flexible electronics being a hot topic, but perhaps lacks killer applications. And so maybe if you could address both what you think the killer applications are and what you think the biggest challenges for the field are.
Thank you. This is a very good questions. And for the killer applications, I think there's actually in the industry, there's already have several fields already have some large quantity of this requirement for the flexible sensors. Actually, for the company we are collaborating with, they have the get more and more demand for this flexible sensing devices. I just give you one example. Is that for example for the wireless earphones, and because this volume is very tiny, so if you make if you use the MIME sensors, it still have the thickness about around the 300 micrometers. But with this thin films flexible sensors, we can make the under about 100 micrometers.
Mm-hmm.
So it didn't occupy any place in your earphones, but it's still working very well. You can see that for the wireless earphones, every cell phone almost require one, so it's a big market. And the biggest challenge, I think, is that to have to go through all these processes, and each steps you have to achieve a very good result, and also get a very so for the every process, if you get the score of the 90%, for example, but 90 times 90 times 90 times 90, then your final result is not very good. So you have to optimize all these processes and get a very good result. It's really a long and difficult time. The biggest challenge, I think, is not only optimize this process, but also to reduce your cost of your whole processes, from the material to the processing and to the packaging and to the testing, and then to the cost very low. So it's comparable to the current MEMS devices and also much lower. Yeah, I think optimize all this process, we can achieve that.
Very good. And I had a question about your interaction with industry. You have very close ties, and I'm wondering what fraction of the problems you address come from either direct questions or challenges posed, and if it becomes difficult ever to be entangled with multiple companies, and it sounds like you also spin out companies from your institute. So can you talk a little bit about how you manage the industrial interactions at your institute and how those get programs going?
Yeah, it's really a good question. I'm actually, my focus is doing the research in our institute. And I think I already working on the flexible electronics for over 10 years. Yeah. So in the later stage, after the publication is getting out, the more and more the people to asking us for the samples, to test in their systems, because they are interested in these directions. But in the early stage, actually, when we give out the samples, one problem is that it's not very good for the applications, because it's not packaged, it's not stable, and the signal is drifting, etc. So about I think 5 years ago, we start to collaborate with some industrial partners to optimize this process. And like you said, yeah, we have the we have the very close collaborators in the industry, and through that we optimize this process together. Then from that we collaborate with other collaborators. Then we make our customer designed the product or the samples for the other collaborators. Through this process, then we keep moving. Yeah.
And in semiconductor processing, there's usually quite a big difference between an academic laboratory using, for instance, small wafers and, not so many steps versus a commercial fab working on 18-inch wafers and, many, many steps and masks and so forth. Is that gap smaller for MEMS? Can you make devices in your foundry that would be, is that part of a manufacturing essentially, or is there still a leap to go from your fab to something that would end up in the device?
Yeah, it's really a good question. I think it's also very important, because in the early stage we're doing our design on the 2-inch wafers to finish our design. But when we go to the foundries, we have to, in the early stage, we have to talk with their engineers to very closely to every step. And because if you move your design to the foundries, the cost is really high. Mm-hmm. We have to, for example, for the one batch of the 6-inch wafers is about 25 pieces. It's a huge cost. So we have to carefully before we move into the foundries, we have to carefully examine, working with the engineering in the foundry together to get the right parameters, so to reduce the cost at this stage. Otherwise, for the research group, we cannot support this process.
Yes, terrific. Well, thank you so much for a wonderful talk and discussion. And it's my pleasure to, well, if we were together, I'd walk across the stage to you. We're just a few time zones and a few thousand miles apart. But thank you for this wonderful iCANX talk and for sharing your work and insight with us. Thank you from all of us.
Thank you very much. Thank you, Paul. Thank you, Alice. Thank
Very
you.
good. Now I think it's back to Alice.
Okay, great.
Okay.
Yeah. Thank you, Paul and Ting. Yeah, wonderful talk and everything. And I hope I can deliver this certification to you in personal. Yeah,
Thank you.
hopefully we can meet sometime. Looks like not, this 2 months. We
Right.
should start in the home for COVID-19. Now looks like a comeback in the winter. Yeah.
Right. Right.
Yeah, be safe and have a good new year. And thank you for your talk. Thank you, Paul. And now I'm going to give some advertisement. Actually, tonight, right now is the last call for the IEEE NAMS conference 2021 and April and Xiamen. So this will be a bigger going together. Now it's the last 20 hours, for the paper submission. So if you're online still not submit your abstract, be sure quickly hurry up. Okay, in 20 hours, submit your abstract online. You're going to hear the plenary talk from Professor Paul, Professor Jagdish, and the 3 Nobel laureates and many, many wonderful speakers on this wonderful conference. Will be hybrid, online and on-site. Yeah, so next week we're going to have 2 speakers for the light. Yeah, one is a young Professor Yuan Mu, young from Tsinghua University. Another is a younger, scientist, Michael Gale Katz is going to deliver a talk here. And Professor Jagdish and Professor Paul will be host of these sessions. And this will be next Friday. Okay, we met at the same time. Thank you so much that our iCANX talks met you every week online. And every week, the wonderful talks, the latest results, and connect world and universe. That's all. Thank you. Yeah, we see you next week.